Um, all right. So, friends, you're about to experience a new kind of class. Now, it's not entirely new. This is a kind of class that engineers frequently have when they're in college, either upper level undergraduate or graduate school. And it's different from any other kind of class in that you're not given stuff to read or listen to and then tested on how much of it you remember. That instead, you will be given some lectures, but you're then going to be asked to use the information that you have, either from the lectures or from outside sources, any source you like, to design a human mission to Mars. Now, and you'll be in a team, probably of 4 or 5 students, and you'll be competing against other teams. Now, we're not asking you to design the spacecraft. We're asking you to design the mission, what actually happens when you get to Mars, to try to accomplish a scientific exploration program that is as effective as possible. And there are limits. There's limits on how much mass you can take with you to Mars. And for example, I don't know, is it 30 tons this time? Right. So think about it this way. You can have more people and more equipment. You have more people, you have more skills, more specialties, but then they'll need more supplies, and that means you get less equipment. Or you can go the other way. Everything is a trade-off. There's no free lunch here. If you want to go strong in one area, by definition, it will weaken you in another. But you have to come up with the best plan. You have to come up, first of all, with your research objectives. What are the scientific questions you think are most important to resolve on Mars? Is it determining whether Mars has life, or is it determining whether Mars has resources for human settlement, or is it something else entirely? So you have to design a research program, and depending upon the research program that you design, you need to choose a place where you're going to land on Mars, because some places are better for the search for life, and other places are better for the search for minerals or other things of that sort. You'll need to choose the optimal crew. You'll need to choose, in other words, how long will they stay on Mars? The longer they stay on Mars, once again, the more consumable supplies they're going to need, and that will take away from, say, the number of rovers you can send to Mars. And are you going to use ground rovers or helicopters or whatever to do the exploration? You'll need to design a life support system for the crew while they're on Mars, a habitat for the crew while they're on Mars, and all this kind of stuff. And then what's going to happen is this. You're going to get a few weeks of lectures and suggestions for background materials. And for example, I've written a book called The Case for Mars, which you can find on Amazon or possibly in the public library where you are. Other experts that are going to talk to you have written articles or books of their own. And by the way, here's another thing. We don't all agree with each other. Okay, some of us think the mission should be long duration stay on Mars, that time on Mars is a fundamental asset. Others want to limit the time on Mars. Some think we need nuclear power. Other thinks we could do it in solar power. There's all sorts of things. There's a different amount of risk people are willing to take. And you see, here's the deal. You have to design the mission. And you'll spend a couple of weeks getting lectures. Then you're going to get a couple of weeks or so. Nicole will tell you what the schedule is. to actually get together and design your mission. Then a week to write it up into a report. And then after you do that, you will present it to a group of judges. Okay. But that are not done yet. Okay, so maybe it's the Monday of, as it were, the final contest week. You present your report. You want to listen to what the other teams present, because the next day you get to attack them. Okay, you will each team will get a half hour on the second day to identify weaknesses in the other team's designs, and bring them to the fore. If you think they greatly underestimate how much their habitat is going to weigh, which means they really won't have that much weight left for their ground rovers, or if anything you can find wrong with their design, you can bring it up. But then on the third day, you will get a half hour to answer all the shots that have been taken at you. Okay. And then the judges will make their final judgment, and you'll get 40 points for the soundness of your engineering design, 40 points for how much science you accomplish, and 20 points for how well you've done with the human factors, the human element of the mission. So that there it is. Now, when you criticize another team, you don't want to criticize them on things that are silly, saying, oh, it really looks stupid, you know, the way you were dressed, or you really stuttered a lot when you talked. No, you want to address weaknesses, actual problems with their design, okay? And people may criticize you mistakenly or unfairly. That's why you get the rebuttal, okay? It's how well you can defend yourself. Another team may distort what you said or meant to make you sound incompetent. Well, then you have to set the record straight, okay? So now, in terms of how this resembles other things, it is frequently the case, in fact, it's almost always the case in a good engineering education, that you have a design class where the class is divided up into groups, and you design something. If you're in aerospace, it might be design a jet fighter. Or if you're in nuclear engineering, it might be design a new kind of nuclear reactor. Or whatever. And then you present it, and then the professors judge you and give your team a grade. Sometimes it happens that a lot of different universities all get the same design challenge, and they come to some central place, and they have, as it were, a tournament where they each present their designs, and the best design presumably wins. Okay, so both of those two things are fairly frequent events within advanced engineering education. What is new here is two things. First of all, we're doing it with you, not with college students. We're doing this with high school, and some of you maybe junior high students. We're showing that you can engage in this kind of thing too. But another thing is this element of criticism and rebuttal. And that, in my experience, is never done with these university engineering contests. And it's unfortunate that they don't do it, because in the real world, when you become an actual engineer and your company is presenting a design, say, to NASA for how to design a Mars mission, some other piece of technology, your competitors are there, and they're telling NASA how wrong you are. They'll be there telling them your design won't work because of this, that, or the other thing. And if anything, it's more cutthroat than this, because in general, they won't make their criticisms of you in front of you. They'll do it behind your back. You have to guess at what they're saying about you to answer it. But here we're going to be a little bit more fair in that any criticism made of your design will be made in front of you and you will have a chance to answer. So that's how this is. This is, you know, engineering in the real world is a contact sport. You know, your competitors are trying to cut you down. So you have to be able to defend yourself. So that's all part of the cut and thrust of this contest, this engineering design challenge. And before I became an engineer, I was a science teacher. And then I went to graduate school and I experienced this kind of class. And I said to myself, this would be a great way to teach high school, because as you'll find out, it changes your relationship to knowledge. In the usual kind of class, knowledge is a burden. How much of this do we need to know for the test? In this kind of class, knowledge is a tool, or even, as it were, a weapon. It enables you to find engineering solutions to make your design work, and it enables you to find flaws in your competitors' ideas. So that's the basic idea here. And we've done this now a couple of times. It's always worked out well. This will be the third time now. And hopefully it will work well here. And this will advance our case. We're bringing this experience, your experience, to schools and telling them, look, here's a better way to teach science. It's much more exciting. It's much more dynamic. It's much more like the real thing. And hopefully we can actually change education by demonstrating the power of this model. So there it is. I'd be delighted to take questions.
If anyone has any questions, you can put them in the chat, or you can just unmute yourself or raise your Zoom hand and ask Dr. Zubrin a question.
No questions?
Not right now. I'm going.
You have one? Do you
I
have a question, Nicole?
No.
All right, well then let me, since I've talked a lot about the contest, let me talk a little bit about Mars.
Okay, I'm going to do a basic Humans to Mars presentation after you speak. Dante has a question.
Okay. Dante?
Go ahead and unmute yourself, Dante.
Yeah, hello, my name is Dante. I have a question. So for the 30 tons, does the rocket, like, I know that we're not designing it, but let's say we want to use it as part of the base. If we were to land on Mars, like we would have the base detached from the rocket. Would that count as the weight as well?
The rocket delivery system does not count as part of the weight. In other words, what you're assuming is that someone has created a system that can deliver 30 tons to Mars. Okay, so, you know, so you've got 30 tons of stuff, which needs to include your habitat. Okay, and if you have a laboratory in the habitat or any other stuff, it needs to include the astronauts, their spacesuits, their supplies, their power system, their vehicles, all that kind of stuff. But the system that delivers you to Mars is not your concern. You've been given 30 tons to do the job, and now you got to figure out how to do the job.
Thank you.
Any other questions for Dr. Zubrin at this time? Okay, did you want to talk about Mars?
Yeah, I do. Now, by the way, what is the schedule here? How long should I talk?
So you're scheduled to talk until 10:30 and 15 minutes of questions. And then I'm going to do a presentation about Humans to Mars and basics about Mars, and go over the syllabus and the rubric from 10:45 to 11:30.
Okay, so here's the thing. Now, you're going to hear from other experts too, and they're going to convey to you what they think are the most important things about Mars. And you're going to have to weigh it because we're not going to agree with each other. But that's how things are in the real world. The real world doesn't give you the answers in the back of the book. You get all kinds of information from different people and you have to sort it out yourself. But from where I stand, okay, I think that there are two things that are extremely important about Mars. And these are the questions of, was there or is there life on Mars? The question of native life on Mars and what that means to science. And then there's the question, will there be life on Mars? What does Mars mean to the human future? Now, Nicole's going to talk a lot about what Mars is like, but I'll just mention briefly, Mars today is a cold and dry planet with a thin CO2 atmosphere. But in its early history, for about the first billion years, Mars had a thick CO2 atmosphere, and that gave it a strong greenhouse effect. And that warmed the planet enough that there was liquid water. So we can see water erosion features all over the place on Mars. Mars had flowing water on its surface. And in this period of time, 3 to 3.5 billion years ago, Earth was actually not very different from that. It also was a rocky planet with a CO2 dominated atmosphere and liquid water on its surface. And life appeared on Earth. Did it also appear on Mars? In other words, did the physical and chemical conditions that led to the origin of life on Earth, since they were similar on Mars, also lead to the development of life on Mars? This is a really important question, because if it's true that life appears from chemistry wherever you have the right physical and chemical conditions, it means that life's all over the place. In other words, if it's a natural thing that happens as a direct effect, like if you leave a cup of water outside on a cold winter night, you come back in the morning, it'll be frozen as ice. And there's no two ways about it. It's not a question of luck. It will be frozen. If this is a natural process that occurs with that kind of certainty, that means life is all over the place in the universe. On the other hand, if the origin of life from chemistry on Earth involved an element of freak chance, that all the different chemicals came together to form this incredible DNA double helix molecule, and it was 1 in a zillion shot, and we lucked out, we could be alone in the universe. So if life appeared on 2 out of 2 planets, then we know that we didn't win the lottery, that it's something that happens to everybody. On the other hand, if the planets were alike, but it didn't happen on Mars, it could mean that Earth did win the lottery and we could be totally exceptional. And we could find that out by exploring Mars. Furthermore, if there ever was life on Mars, while it may have died out on the surface when the surface of the planet became too cold for liquid water, it may still exist underground where it's warmer and there is groundwater on Mars. And if we could send human explorers to Mars and drill down to where the liquid water is, we could bring it up and look at the organisms. We're talking here about microbial life. We're not talking about looking for dinosaurs or aliens. We're talking about looking for microbes. But still, all life on Earth uses the same genetic code, DNA, RNA. It's like it all uses the same language, even though some of us here are microbes and some are crocodiles and some are mushrooms and some are people. It all uses the same information system. If life appeared on Mars, does it use the same information system or does it use a different one? That's really worth finding out, because that will tell us a lot about the potential diversity of life in the universe. And then aside from these natural science questions that people have wondered about for thousands of years, is the universe inhabited? There's the question of the human future. Can human beings become a multi-planet species? You've seen Star Trek and movies like that. People are living on many planets, and it's an open future with many possibilities. Is that achievable? Well, Mars is the most favorable planet in our solar system. for us to go to and give that a try. And if we can't make it there, we can't make it anywhere but here. But if we can, the universe could be open to us. And so the possibility of establishing human settlements, new branches of human civilization on Mars, has tremendous implications for what kind of future humanity is going to have. So both of those sets of questions can be addressed, although not necessarily to each one to maximum advantage, by exploring Mars. You may need to put emphasis on one more than the other. But you're going to Mars, you could find out some of these answers now. Some of the other speakers may come up with different questions. Okay. All right. Any questions now?
And I am Nicole Willett. I am the Director of Education Programs for the Mars Society. I am a science teacher. I teach science full-time, high school. And I am going to share the screen so you can see the syllabus. Can everyone see the syllabus?
Yep.
Awesome, thank you. All right, so this is the schedule. Now this document is live and may change, so make sure you check it every day. I've had some people asking to move schedules, so sometimes, like tomorrow, Chris McKay speaking at 10, but then Ashwini might move up to 10:45. So just check every day the schedule. So we have about 2 weeks. Next week, I'm still scheduling scientists. So next week looks a little light, but actually it may fill in a little more. So whatever time zone you're in, when we started this morning, those are the times we will start. So for 2 weeks, you're going to have lectures. Hopefully by this weekend or the beginning of next week, I'll have you grouped into teams. Then you will start your design activities. So for 2 weeks, you're going to, from July 10th until July 21st, you're going to design your project and you're going to write your paper. That is due by 6 p.m. Pacific time in the US. If you need help with the time zones, let me know. And then Monday, July 24th, you are going to be presenting your design. So I suggest you make a slideshow of some kind to match your paper. Now you will be assigned a mentor also to help guide you through this process. We have some really good experienced mentors. I will also mentor a team, and we have other mentors that will be joining us as well. You will present on Monday, June 24th. You'll have 30 minutes to present your slideshow and your design. And then you'll have 48 hours to get together with your team to discuss the other teams. And then you're going to challenge or attack, as Robert Zubrin said, the other team's designs. If you see a flaw in someone's design, this is your chance to say, you know what, I don't really think that's going to work. Maybe you should rethink that, or say it in whatever appropriate languaging you feel necessary. And then you'll have 48 hours to rebut the criticisms. So your team will also be attacked by other teams. And then you'll have 48 hours to say, maybe they were right. Maybe we should make this adjustment. Or stand up and say, you know what, I'm sticking by my design, and that is what we're going to do. And these are the reasons why. Maybe you didn't fully explain your design in the first on the first day, round one. So then you'll have a chance to expand and explain that. And then the announcement of results will be on Monday, July 31st. Hopefully it might be, we might have a day or two where we need a little extra time for that. So now I'll just show you the rubric. If you don't have these, I believe I shared it with everyone. If you don't have these, please let me know. Email is best to let me know if you're missing something. So The challenge, design a human Mars mission. As Dr. Zubrin said, you do not have to consider the weight of the rocket going to Mars. One of the students asked if you are going to use the rocket as weight for, you know, your 30 metric tons, if you're going to use it as your hab. If your rocket, if your hab is your rocket, you don't have to count the structure of the rocket. That will be the part of the hab for your weight. So the purpose is to accomplish as much scientific exploration as possible. Your team is designing a Mars surface mission, which will include designing its habitat, surface vehicles, scientific instruments, power system, and other equipment and supplies, crew size and composition, mission location, scientific objectives, rations, duration, and exploration plan. Now, there are a lot of articles on marspedia.org. I'm actually really good at answering questions about what you may or may not need to go to Mars, so feel free to email me anytime. Your team will be in science, engineering, and human operation, 3 groups or 3 divisions, depending on how many people end up on the team. You will be up to 5 years on the surface of Mars. You do not have to stay for up to 1.5 years, correction. You do not have to stay for the whole 1.5 years, but you have up to 1.5 years. So you'll have to figure out actual realistic launch windows. When can we launch to Mars and when can we launch back from Mars to Earth? So you're going to have to decide and figure out when those launch windows are. You have 30 metric tons, which we've talked about. You can have up to 6 Marsonauts or astronauts. And then think about who should be in the crew. What are their skills and training? What is their compatibility? Is there a commander or is everybody equal? What type of spacesuits will they need? Water, how much water does a person need for every 24 hours? How will they get water? What kind of food will they eat? Where will the food come from? You have to choose your landing site. Where's the best landing site for a human mission to Mars? What type of vehicles should you have? Power. What kind of power are you going to have? There's no like electrical grid on Mars, so you're going to have to figure that out. Food, bring it or grow it. I think I mentioned that already. And redundancy. So what redundancy is backup systems. So what if you take all your freeze-dried food to Mars and something happens and it no longer exists or it's contaminated for some reason? How will you feed people? Do you have a redundant system for that? Your hab diameter should be 8 meter maximum. So we will be using the metric system. Will you use a rigid structure, a larger structure? If you use inflatables, you can have a larger structure. Life support in the hab and lab space versus living space. What will your, last year we counted the cost in the grading system. So think about how much this may cost, but you're not going to be graded on that. How will you resolve disputes? And what exploration possibilities are there? Dr. Zubrin earlier talked about possibility of life, past or present. That's a big subject on Mars. What will happen if you discover bacteria on Mars? Will it harm the humans that go there? So think about that. Geology, climatology, how will the weather on Mars affect your crew? There are wind, dust storms, and it's very windy, but the atmosphere is only 1% of Earth. So think about that. The dust particles are also very small and can make it challenging for equipment. And then your design report. Designs are to be written in a report format and submitted by the deadline. 25-page limit, 12 font, standard margins, 3 sections, science, engineering, and human operations. They don't have to be even. So sometimes science might be 7 pages and engineering might be 12 pages and human operations might be 4 pages. They don't have to be identically even. Each team member is responsible to write their own portion of the report. You may use publicly available images or draw your own. And your references you must have references. And then your presentation and debates will be July 24th through 28th, which I explained earlier. And then your 100 points will be counted 40 for science, 40 for engineering, and 20 for human factors. We'll have probably 5 or 6 people grading these, and they'll all grade them based on their own reasoning and skill set. And so each team will be graded by several judges, and then we compile all of our grades, and then you get an average from the judges, and that's how we score it. So it's not one person grading this, several people are grading. The syllabus is linked here. Last year's lectures are on YouTube. It might be helpful to watch those. Also, the presentations from the students that came to last year's Mars Society convention in October at Arizona State University, those are also published on the Mars Society's YouTube channel if you want to watch those. This is required viewing, Dr. Zubrin's lecture on Mars Direct. And I'm not going to read the whole FAQ. You can read that at your leisure. I would like to, and if you have any questions, email me, please, and let me share. Any questions about that so far? Go ahead, Annika.
Yeah, thank you. This opportunity is amazing. And I just wanted to ask whether these lectures, like the current lectures, like for example, this one you're giving right now, if the recordings would be available online, because it's really late at this time right now and I'm not sure I'll be able to attend every day.
Of course, yes, that is the reason we record them and then we post them to you. They'll be linked in the syllabus. So today's lectures, as soon as they are uploaded, they'll be linked. They'll be linked in the syllabus so you can go back and watch because everybody's in a different time zone. So yes, they will be recorded and linked for you to watch. And if you can't find it, just email me.
All right, sure. Thank you so much.
You are very welcome. All right, so now I'm going to just talk a little bit. Now this is where we have, oops, hold on, you gotta find the right spot. This is my slideshow about a human mission to Mars. So I will email this to everyone if you'd like. There's a lot of good information in this slideshow. And it's basic information about Mars. So, human mission to Mars. And if you have questions as I go through this, put them in the chat, and at the end, I'll go through and answer them. As I said earlier, I'm Nicole Willett, Director of Education Programs for the Mars Society. I've been serving the Mars Society since 2012, so for a very long time. And it is my absolute pleasure to present this to you now. So the solar system is very big. So they've squeezed it down on this image. This is an artist's rendition. These aren't really to scale at all. But we have the sun, Mercury, Venus, Earth, and Mars, and then the asteroid belt. So Mars is the 4th planet from the sun, and Earth is the 3rd planet from the sun. And these are way farther apart than they look in this image. All right, so the sun is a star. And the difference between a star and a planet is stars make their own energy. They fuse hydrogen at the center, and that's why stars are bright, because they're fusing hydrogen, and that's causing a reaction to make them be, a star and not a planet. They make energy. Planets do not fuse hydrogen. So here is a different image. This may be helpful. So we have Earth and Mars in the orbit. So when I was talking earlier about the launch window, if you can see here, Earth sometimes can be on the right side of the sun, and Mars can orbit and be on the left side of the sun. Well, we definitely don't want to launch when Earth and Mars are way too far apart. So we have something called the Hohmann transfer you might want to look up and figure out when the best launch windows from Earth to Mars are, and from Mars to Earth. So the planet Mars, this is just some history, was named after the god of war from Greek and Roman mythology. It's the fourth planet from the sun. It's known as the red planet. It orbits the sun at an average distance of 150 million miles, or 1.5 astronomical units. Mars is regarded as the second most hospitable planet for the appearance of life. It is half the size of Earth, but if you took all of the landmass on Earth and squeezed it together, it would be about the same landmass that Mars has. Mars year is 687 Earth days. Its day is 24 hours and 37 minutes. You may see 24 hours and 39 minutes because there's a solar and sidereal day, but just know it's 24 hours and either 37 or 39 minutes. The axial tilt is 24 degrees. So Earth's is 23.5. So the axial tilt is what gives us our seasons. So Mars and Earth have the same seasons. It's just Mars's seasons are twice as long. The surface gravity is 1/3 of Earth's, and the temperatures, as you can see, -87 Celsius to 20 degrees Celsius. Those are approximations. So it varies widely depending on what time of day and where you are on Mars. At night, even if it gets 20 degrees Celsius on the equator in the summer on Mars, at night that temperature drops dramatically because there's a very thin atmosphere. Mars does have 2 moons, Phobos and Deimos. They are very oddly shaped, probably captured asteroids. And then geographical features, Mars has a lot of desert areas. North and South Pole are covered in ice caps. Those ice caps are made of H2O ice and CO2 ice. And those ice caps grow and recede as the seasons change on Mars. There's a lot of rocks. You can see here, there's some morning frozen dew that turns into ice on Mars. It has clouds and snow and dust storms. The Phoenix lander that landed, I believe, in 2008, you can look up Phoenix lander snow on Mars, and you can see some video of it snowing on Mars. The Phoenix lander landed at the in the North Polar region of Mars. Geographical features, this is Olympus Mons. It's the largest volcano on Mars, and in the solar system, it is 3 times as high as Mount Everest and the size of the state of Texas in the US. If you stood on this volcano, it's so big, it would look like you're standing on flat ground, even though it's really, really tall. It's just very, very wide. Valles Marineris, or the Mariner Valley, is a 3,000-mile long Grand Canyon-like geographical feature that looks like a giant crack on the surface of Mars. It has many, 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 many craters. The southern hemisphere has more craters than the northern hemisphere. The northern hemisphere probably was covered in water at some point in the history of Mars. And so that may be something you want to look into, because you're going to want to find, where did all that water go? And can we use it? If we find the water, maybe underground, can we use it for our mission? Will it be safe? So many orbiting spacecraft have taken images of dry river channels, and now that we've had landers and rovers on Mars for many, many years, they have discovered lots of evidence of water on Mars. So there is still some debate if water can sit on the surface of Mars or not. There's something called the recurring slope lineae that has been debated widely, whether that is current water flowing on the surface of Mars for brief periods of time, or is it something else? So that's something you may want to look into. If water is on the surface of Mars and it's plain water, it will disappear and evaporate very quickly because there's not enough surface pressure and the temperature is very, very, very cold. So will water be able to sit on the surface of Mars if it's filled with minerals? And we know that there's a lot of minerals in the regolith on Mars. The regolith is the dirt on Mars. So water's everywhere. We just have to find it. We know that the soil, if you scoop up enough soil and you heat it up, you can extract water out of the soil. But is there water in liquid form under the surface of Mars? That's the question. It's very likely that it's there, but you'll have to do some research. It's very cold and windy on Mars. It does not rain now, but it does snow. So this image is from the Phoenix lander that I mentioned earlier, in the North Polar region of Mars. There are dust storms. Oh no, I think this might be a Viking image. I could be incorrect on that. That might be a Viking image. There are dust storms and they may last for months. So if there's dust storm, how will that affect a human mission to Mars? It could cause so many problems: communication, transportation, safety of habitats and vehicles. The dust is very fine. If you've ever baked a cake and you've used flour or cake mix, how fine it is and how it gets everywhere. If you spill it, makes a big mess. That's about the consistency and the size of the dust on Mars. And so it can get in the gears of vehicles. And even if you're in a spacesuit and you have like an articulation, the dust can get in there. And if you're out on a mission and you're getting dust in your gears, how is that going to affect your mission? The atmosphere is very thin. The hottest day is 70 Fahrenheit or about 20 Celsius, but it gets cold very very quickly because the atmosphere is very thin. It's 1/100th the atmosphere of Earth, the pressure. All right, why do people want to go to Mars? For the knowledge of Mars, for the knowledge of Earth, for the challenge, for the youth, which is all of you wonderful students, for the opportunity, for humanity, and for the future. There's a certain number of people who would like to go to Mars to make humans a multi-planetary species. So what would you need to think about if you're making a human mission to Mars? We need to know when we can launch. So here's a little diagram of here's Earth and here's Mars. Well, we need to launch when Mars is back here. And as Mars goes around, we catch it. So we have to find the proper launch window. Why Mars? Mars can be settled. It has enough raw natural resources for humans to go there. It's just, do we really want to commit to doing it? It would be the beginning of humanity's career as a spacefaring species. If you've ever watched Star Trek or even Star Wars or any sci-fi movie where they're going from one planet to another, that's the future we're hoping for. There are no limits to what we can do as humans. We know we've accomplished a lot as humans. And once we get to Mars, it'll be good practice to get to other planets in other star systems later. So what are the top 10 things I think we need for a human mission to Mars? Food, water, houses, vehicles, energy, entertainment, communication, work to do, comforts of life, and personal items, and each other. So why entertainment? Some people have asked me that. Some students have asked me that in the past. Why is that important? Well, going to Mars is very stressful and it's very hard psychologically. So sometimes we want to just think about something that's not stressful for a little while. Like if you guys have ever been, like it's exam week, let's say, and you're very, very stressed out. How nice is it to have something to do, like, play video games or watch a funny movie, something to distract you from the stress of your tests. So entertainment is important. Having human interaction is important. Human interaction, whether it's can be stressful or not, human interaction is very important for us psychologically. Power, so we need to have a source of power. We need to be able to have lights on while we're on Mars at night, or in general, we need to have energy for our computers and for all of the things in our lab to work. So how are we going to get that power? Will it be solar, geothermal? Will we have wind turbines? What type of power will you use? How will you access the internet? That is going to be very important because you will have to communicate. Your crew, when they get to Mars, will have to communicate with Earth, because what if there's an emergency? What if somebody needs surgery? There's a million different reasons why you're going to need internet access. We send signals and information to and from Mars all the time using a series of orbiters that orbit the planet. Houses. So this is an example from NASA of how what their habitats look like. So when I said earlier, if you make a solid habitat, it can only be 8 meters in diameter. So that would be an example of this right here. This is what that is. It's made of steel or some type of aluminum or metal, something. But if you make a habitat that's inflatable, and you basically can make a very, very, very big habitat for this mission. So you have to decide what's better. Do you want the smaller 8-meter diameter, or do you want the inflatable habitat? And then this is an example of if you landed several spacecraft and those were your habitats. A student asked me that earlier. You could connect them all together and make a big, big, big habitat over time. The more you land, the more you can connect them. 3D printing. This is an idea that's been proposed. They're using it here on Earth. They're also proposing it for moon missions and for Mars missions. You can see the structure of the 3D printer doesn't seem that difficult to manage getting to Mars. So if you took these parts to Mars, assembled them there, you could have them automate an automated system to assemble them. Then you could use the regolith on Mars and some other cement binding material and 3D print any type of habitat you want, or tools or furniture or other machines or vehicles. Greenhouses for plants. You're going to need a way to get food, especially if you're going to be on the surface for a year and a half. It's a good way to get food, and it's a good way to get an extra source of oxygen, because as you know, photosynthesis, plants take carbon dioxide from the atmosphere and produce oxygen. And then you'll need some type of vehicle to travel in to go do science. So you'll have to have some type of vehicle. There are many prototype vehicles for Moon and Mars travel. They could be sent ahead of time in a separate spacecraft. Your 30 metric tons does not have to be one trip. You can split it up into 2 trips. And oxygen. How would we get oxygen? So you can, there is a mechanism on Mars now on the Perseverance rover called MOXIE that is taking air and turning it into oxygen on Mars. And it's kind of a test to see if we can take air from Mars, the atmosphere from Mars, and split it apart and make breathable oxygen, and it's working. So you'll have to figure out how much oxygen does a human need to breathe if they're there for a year and a half. And if you have 6 humans there for a year and a half, how much oxygen will they need? and creating an atmosphere. So this would happen long term if we were on Mars long term. There are many ideas about creating a thicker atmosphere for the pressure on Mars, because you would have to, your crew will have to wear a spacesuit because there's not enough atmospheric pressure. If you've seen the movie Avatar, the pressure on that moon, Pandora, is the same. So they don't have to wear a spacesuit on Pandora, but the humans do have to wear like an oxygen mask. Hopefully someday we'll get to a point on Mars where we will have created a thicker atmosphere where humans won't have to wear a pressure suit, and maybe just an oxygen mask. Or maybe we can produce enough oxygen that we won't need that at all. But this is kind of an example of long-term terraforming Mars and creating an atmosphere. And then heat, again, energy, how would we keep our astronauts warm? Because it gets very cold there. Same thing, what would you use? Solar, geothermal, wind turbines, or you have another idea. Gravity, so you would have to think about bone and muscle mass loss on the trip to Mars and on Mars. So this is another human factor you're going to have to think about. Astronauts, when they go to the space station, if they're there for 6 months, they can lose 40% of their muscle mass, and bone can decrease rapidly. So you have to have a way to keep your body strong. You definitely don't want to lose a bunch of muscle mass and then come back to Earth and kind of be incapacitated. So you have to think about that. All right, why do we want to go? For the knowledge of Mars, Earth, the challenge, the youth, the opportunity, humanity, and the future. So this is the key to unlocking the secret of life in the universe. It is the challenge to adventure that will inspire millions of young people to enter STEM subjects and careers. And this will reaffirm the nature of society as a nation of pioneers, and will open the door. Oh, something's happening here. To a new future for humanity. All right, so here is my contact. Please email me after we're done here. If you have a question about the rubric, about the syllabus, anything, please email me. I'm on Pacific time, so I usually answer emails till about 9 p.m. Pacific time. Otherwise, it will be the next day. All right, questions. How is Mars's temperature range like it is when it's further away from the sun than Earth? So it depends on where you're at on Mars, just like on Earth. In the northern hemisphere on Earth, we have summer when we are further from the sun because we are tilted towards the sun. So you have to think about that. So Earth is tilted towards the sun in the northern hemisphere in the summer, but it is further away from the sun. So it'll be similar. Thank you so much for this session and your interactivity. I'm going to be, okay, thank you. All right. If you were to 3D print houses, wouldn't the storms blow them down? No, good question, because they, let me stop share here. Because the atmosphere on Mars is 1/100th. So if you wave your hands around like this, you can feel the air. The air on Mars, for every molecule you're feeling on your hand, there's only 1 out of 100 on Mars. So, and we 3D print houses on Earth and the wind doesn't blow them down. So 3D printing can print pretty substantial homes, buildings. They're solid. It's like concrete is what they're making. Let's see. If we were to sublimate both polar ice caps on Mars via nukes or any means, would we create an atmosphere? Yes, we would. We wouldn't create an atmosphere. We would thicken the atmosphere that is already there. Yes. Yes, yes. Very good question. Any other questions? how would we thicken the atmosphere? So we could nuke the polar ice caps, which I'm not really a fan of personally. We could plant algae everywhere, which would spread pretty rapidly. Some type of genetically modified algae that could sustain the high UV radiation there. That would produce oxygen for the atmosphere and possibly thicken the atmosphere. We could pump out more carbon dioxide. We know how to warm planets. We are warming Earth now. So we could use some type of factory to basically pollute the atmosphere, kind of like we're doing here, and make it warmer and thicker, because that would melt the ice caps. So short term, if you want to thicken the atmosphere short term, nukes would be good, right? Because it would happen fast. They would sublimate and the atmosphere would get very, very thick very fast. But do you really want to colonize a planet you had to nuke to warm up? Long term would be something like the factories, the algae, and things like that. And I'm sure there are many other ideas. I think that anything you do fast, like nuking, is going to probably create a cascade of other problems. How strong winds blow, and does our skin protect us from sun rays? You mean on Mars? So the wind is fast. So if you've seen the movie The Martian, the wind wouldn't have really knocked all that stuff over that way because the atmosphere isn't really thick enough to do that. So Earth has a magnetosphere that protects us from sun rays and an ozone layer. Mars doesn't really have that. So that is why we would need to be fully suited anytime we went outside. Any other questions? Does it hail on Mars? So what we know from the last time I've checked, it snows. I don't know that there's enough. I don't know that there's enough moisture in the atmosphere for hail to form. Good questions. There been any signs of life on Mars? Oh, my favorite question. This is my specialty area. This is what I've researched a lot. I believe that it is 99% chance that there is microbial life on Mars. There are a lot of pieces of evidence that show that all of the parts that we need to have life exist on Mars, all of the molecules, all of the elements are all existing on Mars. There's very likely, if there's life there, it's probably underground. And we need to, dig underground to find it. So yes. You can melt the ice to get water and filter it out. Yes, you can. We just want to make sure that if we go to Mars and we use the water that we may find underground, probably find underground, we need to check it for contaminants and bacteria, because we don't want to use water that has something that may make us really sick when we're there, because we're very far from home. It takes 6 to 7 months if you have the right launch window to get to Mars. So the question is, how long does it take to travel to Mars? 6 to 7 months in the right window, the right launch window. You're welcome. So later today, the person who's supposed to talk next at 1:30 Pacific time, perfect segue, 1:30 Pacific time, which is in 2 hours and 15 minutes from now. That person has been traveling And I am hoping they're scheduled to talk at 1:30. I'm hoping they'll be here. I will be here to open the room for them. If they don't make it because of their travel schedule, we can just do Q&A. And if you'd like, I can show, maybe some videos from last year if they aren't available, but they're supposed to be here. They are scheduled at 1:30 Pacific time. Anything else until 2 hours and 15 minutes from now? Is there any chance to schedule earlier? Well, the reason they're scheduled the way they are, it's early Pacific time. We start at 10 a.m. The problem is the scientists are also all over the world and the students are all over the world. So we kind of had to make it as early as we could Pacific time. I realize, some of you are, might be the middle of the night, and I apologize for that. You do not have to join live. These recordings will all be posted as links in the syllabus as the weeks go on. If you're too tired, if it's the middle of the night, I totally understand. But we wanted to open this up to as many people as we could around the world. Oh, I'm so sorry. Let's see. And how much time do you think humans will be able to live on Mars? Well, we have the technology to go to Mars right now. It's just, we haven't done it. There's a lot of money and politics involved. And so that has stopped us from doing it. But right now, I think SpaceX has a pretty good chance of getting us there. But to live permanently on Mars, I think we have the ability to do it, maybe 20 years. If we launched next year, which isn't planned to go to Mars next year with humans, let's say we launch next year with a first crew of humans to Mars and it was successful, and then say we launched, the next launch window would be in 2 years, say we launched 3 crews in that launch window, then they could start really setting everything up for humans to live there permanently. Is the weight for travel a part of our specified weight limit? No, you do not have to count the weight of your rocket or your fuel. The people that go to Mars will need food and water as they make their way to their destination. Yes, that weight will be part of your total. Yes, yes, it will, but not the rocket. If you're using your rocket as your hab, that does not count towards your weight total, but everything inside of it and the people and the food and the other equipment does. Anyone else? I will forward. Oh, do you think Elon Musk SpaceX? Yes, I do think SpaceX has the best chance right now of being successful. You are welcome. I will send you the, do you guys want that slideshow? Do you want a copy of it? I can send it to you. It's a PowerPoint, but you can open it in Google Docs or Google Slides. How much does the average spacesuit weigh? You are going to have to look that up because there's a lot of different options. So if you want the slideshow, type yes in the chat and I will send it to you. If you don't need it, that's fine, because it'll be on the video. Share the recording. We will, as soon as it gets uploaded, we will share it on the doc. Okay, and I will send the slideshow. All right, awesome, awesome, awesome. Please email me anytime with questions. Give me, well, I'll see you guys in 2 hours and 13 minutes now. Okay. Thank you. I'll see you guys in a little while. Bye. David, why are the SpaceX suits so small? Technology has allowed them to reduce the size, and we need more dexterity. All right, everyone. I'll see you in a little bit.